The Milky Way is a tremendous structure in space containing billions of stars and trillions of planets. In their turn, these objects are surrounded by gigantic clouds of interstellar dust and scorching hot gas streams. All these components make up the bizarre and fascinating picture called galaxy. And today, we invite you on an exciting journey across it.
Stars are awesome. Since mankind first became able to comprehend our existence, we've looked up at the night sky and seen these distant glimmers of light, and they've shaped our culture, religion, and scientific progress. While you can only see a handful of stars with the naked eye, the universe has more stars than one could possibly imagine, shining and radiating light and heat throughout entire galaxies, and they provide the essential warmth that cradles life. All life on Earth owes to the sun. Even the animals at the sunless depths of our ocean would not exist were it not for the sun's gravity and the dust that once surrounded it, forming the ground we now stand on. But putting its existential considerations aside, how do stars actually work? Why is it that the universe is so full to the brim of hundreds of sextillions of stars? What makes them so common, and why are they so massive and powerful? Well, to understand the answer to these questions is to understand creation, and the story of a star from birth to death is unparalleled in astronomy. Today, we'll be journeying back billions of years as we uncover the mysteries, wonders, and timelines of our own sun and the other stars that characterize our galaxy and the universe. Firstly, before we begin to look at how they form, what exactly is a star? Well, in short, stars are massive spheres of matter in plasma state, essentially a giant continuous explosion of molten soup, held together by its own gravity. Stars are powered for the vast majority of their lives by nuclear fusion, an energy generating process we are trying to recreate here on Earth to solve our energy demands. For about 90% of a star's life, it turns hydrogen into helium at its core, and the energy this releases moves to the surface and emits stellar radiation. When it comes to our own sun, we call this emission solar winds, light, heat and matter radiating across space over billions of kilometers for billions of years at a time. Stars are the most massive component of any given stellar system. Like our own solar system, the sun accounts for over 99% of the mass of everything in our solar neighbourhood, and as such we often use measurements of the sun's mass to estimate and categorise the weights of various other astronomical features. The mass of our sun is approximately 1.989 times 10 to the 27 tonnes, which is a number I'm not even going to try and pronounce. However, this figure characterises one solar mass, a unit of measurement we use to assess the mass of other stars to that of our own, and we'll be using this measurement a lot today. There are estimated to be as many as 300 sextillion stars in the visible universe, that's 3 with 23 zeros. Approximately 2 to 400 billion of these stars lie within our own galaxy, the Milky Way, and each mature galaxy usually has anywhere between 100 billion to 100 trillion stars. Around 2,000 of the stars in our own galaxy are visible from Earth in the night sky, with these particularly bright, local and luminous stars being grouped into shapes that resemble humans, objects and animals, known as constellations, which are really useful when it comes to mapping the positions of these nearby stars. Stars can form in groups of dozens, hundreds or thousands, and these can form star clusters. Thanks to the gravity of these clusters, and with a bit of help from dark matter, these clusters then combine to form dwarf galaxies, and the dwarf galaxies then combine to form spiral galaxies, such as the Milky Way. Spiral galaxies retain the hydrogen and helium gas clouds that formed the earliest stars, and as such these spiral galaxies are essentially gigantic star-producing factories. These galaxies then collide to form giant elliptical galaxies, where some of the highest concentrations of stars in the known universe are found. But thinking smaller than star production on a galactic scale, how does an individual star actually form? Well, its life cycle is fascinating and can be broken down into 4 main stages. Star formation begins with molecular clouds. These are clouds of dust and atoms that have been around since the earliest days of the universe, and they have higher densities than their surrounding space, and so are held together by their own gravity. These clouds consist of mostly hydrogen, the most abundant element in the universe, and usually about a quarter helium, with a small fraction consisting of a few other heavier elements. These clouds come in many different shapes and sizes. One such form is nebulae. The Orion Nebula is a giant star-forming region in the constellation of Orion's Sword, which is visible from Earth. Other areas of star formation include the interstellar medium, clouds of hot gases and atoms that occupy the space between stars in galaxies, and in certain regions of colliding galaxies where multiple hot gas clouds collide, invariably making them much more productive, often forming what is known as a starburst galaxy. No matter what form these clouds take, eventually they collapse into a dense core due to their own gravity, and this gravitational energy then turns to heat. When this collapsing cloud reaches a relatively stable point, the embryo of a star forms, known as a protostar. These infant stars are then cooked in this giant gaseous oven forming around it, trapping more hydrogen and helium within the core. This process of incubation in this manner takes about 10 million years, and when the protostar is sufficiently developed, it begins to emit plumes of gas, which, alongside external radiation, helps to drive away the gas clouds around the outside, essentially the shell of the star. These shell gases that are driven away are mostly dust, and are ejected outwards but still orbit this new star. This dust begins to clump together, forming rocks, and these rocks smash together to form planetary embryos, which have the potential to become planets. Earth was formed in this way after the Sun formed, and complex carbon chemistry did the rest. So essentially, we all came from stardust once. This is the beautiful process that fragments massive gas clouds, turning them into dozens, hundreds and thousands of new stars, with child planets to watch over and keep warm. These stars are then ready to enter the next phase of their lives. However, not all stars get this far. Those stars with a particularly low mass, more comparable to the mass of Jupiter than the mass of the Sun, are unable to sustain nuclear fusion of hydrogen in their cores, an essential process for a star in the main stage of its life. These light stars can, however, fuse lithium, and instead of becoming a star, they become what are known as brown dwarfs. Contrary to the name, they often appear magenta in colour, and often sit somewhere between extremely large gas giant planet and extremely light mass star. They also typically have no difference in structure between their cores and their outer layers, and so these failed stars never get to become the giant radiating beacons we see in the night sky. But for those that are massive enough to sustain their fusion reactions, these stars burn away their incubating molecular ovens and enter the second and main stage of their lives, the thermonuclear fusion stage, otherwise known as the main sequence. The main sequence accounts for about 90% of a star's lifespan, and is the point when fusion begins to take place, with the vast quantities of hydrogen that has been trapped in the core being fused into helium, releasing massive amounts of energy. This is what gives stars their immense heat, blinding light and incredible radiation that travels billions of kilometers across the near vacuum of space. A star that has just entered the main sequence is usually in the form of a dwarf star. The Sun is a main sequence yellow dwarf star currently. These stars are small compared to some of the other older stars, and contain much more hydrogen than they do helium. However, fusion converts hydrogen into helium, and so the share of helium within the star begins to rise. This increases not only the brightness and temperature of the star itself, but the rise in helium also increases the rate of fusion in a somewhat compound process. This process, coupled with the emission of solar winds and radiation, causes some mass to be lost. However, this usually equates to only about a fraction of a percentage of the total mass over a star's entire life, so it's nothing to worry about. However, much more massive stars can lose a more significant percentage of their mass during the main sequence and beyond because they are much less efficient. How long the main sequence lasts for depends on the size and mass of the star and the amount of hydrogen that star was formed with. Our Sun is expected to live for around 10 billion years, whereas some supergiant stars with more mass will be considerably less stable and last nowhere near as long. The smallest possible main sequence stars are known as red dwarfs, and these can fuse all of their mass fairly efficiently, and so stand to live the longest. We don't know how long for sure, but we theorise that it could be up to 1 trillion years. When these smaller and less volatile stars have burned up their hydrogen, they will collapse into white dwarfs and the temperature will fall, circumventing any other post-main sequence process. As for the more massive stars, these are less efficient and less stable. They fuse their hydrogen at a certain pace and can last for billions of years, but after the hydrogen fuel at the core has been used up, helium will start fusing into carbon, and this is where things start to get interesting. If a star is approximately 40% of the mass of the Sun or above, Then when the hydrogen fuel within the core is exhausted, the star will begin to fuse hydrogen outside of the core, which is now all helium. Heavier elements are being fused in the core as a result, and these newly fusing outer layers expand and cool down, dramatically increasing the star's size and giving it a red colour. It has entered the red giant phase. This is the stage we all love, because it is the stage that forms the titans of the galaxy. The size of the star in its red giant phase depends on its mass, but regardless, it is ironic to think that when a star grows to become a giant, it is actually in the stage of its life where it's starting to die. Our sun is no
And whenever some of them are solved, they add to our knowledge about the universe around us. Are we to solve all its mysteries someday? Time will show.